In part 2 of this lecture, we'll spend some time talking about conjugate acid-base pairs. A conjugate acid-base pair consists of two molecules or ions that are related by the presence or absence of an H plus ion. The best way to illustrate this is with plenty of examples. So here we go. What we have here is an acid. It's acetic acid, and what we'll call its conjugate base, which is the acetate ion. I want you to see that these two different species are related by the presence or absence of an H plus ion. Acetic acid has the H plus ion. The acetate ion does not have the H plus ion. So acetic acid we would naturally call an acid, so we're going to say its conjugate base is the acetate ion. This may still not be a good enough explanation for you at this point, but just zero in on the fact that these two things are related by the presence or the absence of an H plus ion. So they are a conjugate acid-base pair. We would say that the acetate ion is the conjugate base of acetic acid. How about if we wrote this ratio in reverse? So I'm going to put the acetate ion on the left and the acetic acid on the right. Now, we've identified acetate as something that can act as a base. So if we identify it as a base, its conjugate acid would be acetic acid. Again, these are conjugate acid-base pairs because they are related by the presence or absence of an H plus ion. So here we would say that acetic acid is the conjugate acid of the acetate ion. Both of these examples are saying the exact same thing. They're just stated differently or labeled slightly differently, but they're both the same conjugate acid-base pair. Let's look at another example. The hydronium ion, which we'll label naturally the acid, and we'll say its conjugate base is water, because the relationship between these two is that the hydronium ion is water with an H plus, so it has an H plus. H2O is missing that H plus, so we have a conjugate acid-base pair. So we'd say that water, H2O, is the conjugate base of the acid H3O plus. It would also be okay to say that H3O plus is the conjugate acid of H2O. How about H2O and hydroxide? So we'll label H2O here the acid and hydroxide its conjugate base. This makes sense. Here, water in relation to hydroxide has an H plus. Hydroxide's missing the H plus. That's why it's hydroxide. So we say that hydroxide is the conjugate base of the acid H2O. It would also be okay to say that H2O is the conjugate acid of hydroxide. What I've done here is said that you could put the word conjugate on either side, but we've always consistently labeled the acid, and the base, when we're comparing two different species. How about the ammonia-ammonium ion pair? Well, ammonia, remember, acts as a base, and its conjugate acid would be the ammonium ion, because the ammonium ion has an extra H plus that's missing from the base. We say the ammonium ion is the conjugate acid of the base ammonia, and it would also be okay to say that ammonia is the conjugate base of the ammonium ion. Every acid has a conjugate base. Every base has a conjugate acid. Conjugate acid-base pairs are important to notice in acid-base reactions. You may say that this is some sort of chemical trivia that doesn't seem to be all that important. It will become very important, and it will help you to do calculations or set up calculations in future questions if you can identify the acid-base chemistry that's going on. It makes the calculations much easier. Being able to recognize conjugate acid-base pairs will make the calculations easier. So let's apply this concept, this conjugate acid-base concept, to the acid-base reactions we've already discussed and to some we have not. Here's one we've discussed before. We said if you take acetic acid and you dissolve it in water, that there's an acid-base reaction where acetic acid acts as the acid, surprise, surprise, and here's its conjugate base, the acetate ion on the other side. Water here, of course, is acting as the base because it is accepting an H plus from acetic acid. And on the other side of the equilibrium sign, we have the conjugate acid of water. The conjugate acid of H2O is H3O plus. And over here, we'll just specifically identify the conjugate acid-base pairs in this equilibrium. So we have acetic acid acetate as one conjugate acid-base pair, and H2O H3O plus is the other conjugate acid-base pair. You might ask, well, why couldn't we label acetic acid the conjugate acid and H3O plus just the acid? Well, we could, but by convention, since we read reactions generally from left to right, we consider that being the forward reaction. The tendency is on the left to identify the acid and base, and on the right in the products to identify the conjugate acid and the conjugate base. Let's look at another example. Remember, if ammonia dissolves in water, it forms ammonium ions and some hydroxide. There's an equilibrium formed here. But in any case, ammonia is the base. Its conjugate acid would be the ammonium ion. And water here is acting as the acid because it is supplying an H plus to ammonia. And of course, the conjugate base of water would be the hydroxide ion. So our conjugate acid-base pairs here are ammonia and ammonium ion, and water and hydroxide ion. How about reacting if you recall, the strong base hydroxide ion with the weak acid, acetic acid. Now, we won't label these necessarily as strong and weak here. We'll talk more about that soon. Remember, this reaction pretty much goes to completion, so I don't have a equilibrium arrow there. In any event, on the left, hydroxide is naturally the base. Its conjugate acid on the other side is water. Acetic acid is, surprise, surprise, the acid, and its conjugate base on the other side would be acetate. So our conjugate acid-base pairs in this reaction are hydroxide and water and acetic acid and acetate. And finally, here's one that you haven't seen before. What happens if we react nitric acid with a hydrogen phosphate ion? Well, if you do that, there is an acid-base reaction. The nitric acid donates an H plus to the hydrogen phosphate ion to leave nitrate in the dihydrogen phosphate ion. This reaction goes to completion because it turns out nitric acid is a strong acid. Hydrogen phosphate ion is acting as a weak base, and so the strong acid drives this to completion. Again, we'll get more into strong and weak soon. For now, we label nitric acid as the acid. Its conjugate base on the right is nitrate. The hydrogen phosphate ion is acting as a base. Its conjugate acid is dihydrogen phosphate ion. So our conjugate acid-base pairs are nitric acid nitrate and hydrogen phosphate dihydrogen phosphate. One thing that will be important to realize is that the stronger the acid, the weaker its conjugate base, and the stronger the base, the weaker its conjugate acid. Let's give an example of how we might go about describing this. Here's a reaction that we've looked at before, the reaction of the strong acid HCl with the strong base sodium hydroxide, giving sodium chloride in water. We've said before this reaction goes to completion. Let's rewrite this reaction, and this time let's just leave out the sodium ions, which are spectators here. And admittedly, they're not the only spectators, but we're going to leave out the sodium ions and rewrite this equation. So what we have here is the strong acid HCl reacting with the strong base hydroxide, which is the strong base from sodium hydroxide. And over here, we're producing chloride ion. I'm leaving the sodium ion out, remember. Chloride is the conjugate base of HCl, and it's a weak base. And the other product is water, of course. Water is the conjugate acid of hydroxide, and it's a weak acid. Now, one thing you might ask is, how do I go about finding out whether something is a strong acid or a weak acid, a strong base or a weak base, and if so, how weak, or if so, how strong? I figure from the textbook by Brown, Chemistry, the Central Science, has a nice figure that has acids in order of acid strength. So in the red here, the acids, you'll notice acid strength is increasing, going up, and it labels HCl in the strong acid category. So I wrote that right there. And right next to the acids, and these are all lined up for a reason here, are a lot of ions and molecules that can act as bases, only in this case, the strongest bases are on the bottom. So if we find hydroxide, we'll notice that hydroxide is in the category of strong base. Now, how about the two products? Well, chloride, I said, was a weak base. It's the conjugate base of HCl. Let's find chloride on the base side. Chloride is the weakest base. So remember, weak bases are on the top of the bases listed. And I said water is a weak acid. And so let's look in the acid column, and we find water here as one of the weakest acids. So that's how I knew how to label these. Let's look at this chart just a little bit more here. This chart is lined up so that an acid is across from its conjugate base. Or if you want to think about it the other way, the base is across from its conjugate acid. So every single one of these conjugate acid-base pairs are listed here. Hydronium ion is the acid, its conjugate base would be water. The other thing you'll notice that is a little confusing at first is that some things are on both lists, and so you might ask, how could something be both an acid and a base? Well, remember, water can act as an acid or a base depending on the circumstances it finds itself in. There are other ions and molecules that have that same ability. Let's find water. When water acts as an acid, meaning as an H plus donor, it's a weak acid. Well, how about if water's acting as a base? Well, if water's acting as a base, it's a weak base. So it's not a very good H plus acceptor. So water's in both lists. So when it acts as an acid, it's a weak acid. When it acts as a base, it's a weak base. Well, what's something else that's on both lists? Well, here is H2PO4-, that's dihydrogen phosphate. Well, when it acts as an acid, which means it would donate an H plus and form its conjugate base, HPO4 2-, it's a weak acid. However, H2PO4- could act as a base and accept an H plus and form H3PO4 phosphoric acid. So dihydrogen phosphates on both lists, and when it acts as an acid, an H plus donor, it acts as a weak acid. When it acts as an H plus acceptor, it acts as a weak base. Now hang with me here. Let's go back to this reaction here where we said the strong acid HCl reacts with the strong base hydroxide to make the weak base chloride and the weak acid H2O. We know what labels to put on these from this list. Notice I said this reaction goes to completion. One way you can think about this is that let's suppose chloride decided that it did want to go back to the form HCl, meaning the reaction would be reversed. So chloride would have to abstract an H plus from water to reform HCl, and the water would then form hydroxide. Now this has very little tendency to occur. That's why there's no equilibrium sign here. Chloride ion has very little affinity for H plus. Why? Because chloride is a horrible base. It's a horrible H plus acceptor. So it's a weak H plus acceptor. And on top of that, so it's not going to go after the H plus on the water very vigorously. And on top of that, water, because it's such a weak acid when someone asked it to act as an acid, water has very little ability to even assist chloride in obtaining the H plus. Its water itself is a very weak H plus donor. So that's why we can write this equation with a single arrow, because there's really no tendency, or such a small tendency that it's not significant, for this reaction to go in reverse. Again, we can use a table like this to tell us that. So, consistent with what's on the table, chloride, listed as having negligible basicity, is on the right here, and H2O is listed as being a very weak acid. There's no tendency for this reaction to go backwards. Let's talk about a couple other things regarding this reaction. The very strong HCl, right here, has the very weak conjugate base chloride. So I mark HCl is a very strong acid on this list. Its conjugate base over here is the weakest base on the list. Remember, we said the stronger the acid, the weaker the conjugate base. The very strong base OH- has the very weak conjugate acid H2O. So here I show you where hydroxide is on the list. It's a very strong base on this list. And its conjugate acid H2O is a weak acid on the list. The stronger the base, the weaker its conjugate acid. So now you might ask, as you've probably asked before, is this useful for anything? Well, glad you asked. Let's look on the next slide. It turns out that acid-base reactions tend to favor the direction that produces a weaker acid and a weaker base. Now, without stating it as such, we already illustrated this on the previous slide with our reaction between the strong acid HCl and the strong base hydroxide. If you look on the list here and you say, well, what is this reaction going to produce if it does go to the right? It's going to produce chloride, which we label as a weak base, and it's going to produce water, which we label as a weak acid. The water is the conjugate acid of hydroxide. Now, I'm not calling it this here because I want to emphasize that it's weak. But in any event, what we've done is we've gone on the left from a strong acid and a strong base to, on the right, a weaker base and a weaker acid. So acid-base reactions tend to favor the direction that produces a weaker acid and a weaker base. And in this case, the differences between strong and weak are so large that we write this without an equilibrium sign, because there's a very strong tendency for it to go toward the right, toward the weaker base and the weaker acid. Let's try a different example. Suppose I asked you if you tried to react dihydrogen phosphate with the carbonate ion, would that reaction be predicted to react to any significant extent? In other words, what I'm asking you is, would these two react and go to the right? So let's identify what's going on here. The dihydrogen phosphate, if it goes to the right, would be acting as an acid, and we label it here as a weak acid. The carbonate ion would act as the weak base, because here it is here, it's a weak base. You might ask, well, how did you know that H2PO4- was the acid and carbonate was the base here? Well, carbonate would have a hard time acting as an acid. It has no H plus to give anyone. So by default, this is the base, which would make that the acid if a reaction occurs. Well, you can see that since both of these are weak, we stated in the past that a weak acid, weak base reaction doesn't go to completion. So I'm going to put an equilibrium sign here. If they do react, what would they form? Well, the acid would lose an H plus and form hydrogen phosphate ion. And hydrogen phosphate ion, which is the conjugate base of H2PO4-, is a weak base. Let's find it in the base chart. It's right there. And the other product, if an H plus is donated from H2PO4- to the carbonate, would be hydrogen carbonate. That's the conjugate acid of CO3 2-. Let's find this on the acid chart, and it appears here, and so it's a weak acid. Now remember, we're trying to ask, does this reaction really go to the right to any significant extent? In other words, when equilibrium is reached, which side is favored, the left or the right? Well, remember, acid-base reactions tend to favor the direction that produces a weaker acid and a weaker base. So according to the figure on the right, HCO3-, which we labeled a weak acid here, is right here, is a weaker acid than H2PO4- on the left. So here's HCO3-. It is below H2PO4- on the list. So this is a weaker acid than this one. Also, this HPO4-2-, which we've labeled the weak base on the product side, so let's find it here, HPO4-2-, is a weaker base than the base on the left, the carbonate. Let's see, HPO4-2- is above carbonate, which remember on the base side means that HPO4-2- is the weaker base. So we would expect this reaction to proceed to the right toward products and favor the right side, because the right side has the weaker acid and the weaker base than the left side. But that's probably as much as we can say here. These acids and bases are pretty close in strength on the chart, and so we might say it would slightly favor the right, but we don't know by how much. Here's one more example. Would the acid and base shown below be predicted to react to any significant effect? Well, remember, ammonia is a weak base, and we talked about that before, and water then is acting as an acid, and it's a weak acid. All right, let's look on the chart. Where's ammonia on the base category? Here's ammonia. It's in the weak base category. Here's water. If it's acting as an acid, it's certainly weak. If these react, they would go to some sort of equilibrium, but if they did react as a base and an acid, you'd form the ammonium ion. Water would transfer an H plus to ammonia to form the ammonium ion, and what would be left is the hydroxide. Now the ammonium ion, which is the conjugate acid of ammonia, ammonium ion, let's find it on the list. It's a weak acid. We know about hydroxide. Hydroxide's a strong base. We know that. Hydroxide's the conjugate base of H2O. So what would we say? Well, according to the above figure, I think you know what's going to happen here. The ammonium ion right here is a stronger acid than H2O. Here's the ammonium ion. It's a stronger acid than H2O. Just remember, the stronger acids are on the top. And of course, the hydroxide ion is a stronger base than ammonia. It's below ammonia on this list, and remember, the strongest bases are on the bottom. So what we'd say here is that when this equilibrium sets up, it would probably favor the left side. In other words, it would favor ammonia not reacting very much with water to form ammonium ion and hydroxide. Now, if you recall, this is consistent with how we previously described this reaction. Ammonia is only a weak H plus acceptor in water. When equilibrium is reached, only a small fraction of ammonia reacts with water to form ammonium ion and hydroxide. Your head may be spinning at this point, but I just want to remind you that getting a handle on these concepts really will help you set up acid-base problems and do calculations. But the calculations are very difficult, or are much more difficult, if you don't have a handle on the chemistry that's going on in the solution. If you don't have a handle on the chemistry, or at least start to have a handle on the chemistry, setting up these problems you'll see soon will be more difficult. So this is worth spending a little time thinking about.